So let's talk about apparent weight on the surface of the Earth. And so this is the Earth, and it spins, and you could have giant people like this standing here. And so it turns out that the apparent weight, what they feel at is different at different locations. So what the heck is apparent weight? So let's start here with this elevator that has a zero acceleration, so it's just standing there. Well, what forces are acting on that person? There's only two. There's the downward gravitational force, mg, and then the upward pushing force from the surface, n. And you see, since the acceleration is zero, F net is equal to zero. So n plus mg equals zero. This means that the normal force, that we call this the normal force because it's perpendicular to the ground, has to be equal to the weight. And this is what you normally feel. You're just sitting there, you just feel normal. But that's not why it's called normal. It's called normal because it's perpendicular. Now let's imagine that the elevator is accelerating up. In that case, we still have two forces. We have the downward gravitational force, and it's the same as it was before. Maybe I didn't draw it completely the same. It's the same because what is the gravitational force? The gravitational force is an interaction between the person and the Earth. The person and the Earth both have mass, and so really it's this. The magnitude of that's going to be g, mass of the Earth, mass of the person, over r squared, where r is the distance between the person and the center of the Earth, which it doesn't really change. Actually, all this stuff doesn't change, and we call that, that's the gravitational field and has a value of g. Okay, so on the surface of the Earth, that's pretty constant. So, but the mass didn't change and the Earth didn't change, so that can't change. But F net has to be equal to ma, so it has to be some positive value. And the only way for that to work is if the normal force increases. If the normal force is greater than the gravitational force, then you can have a net force up and the person will accelerate. And I don't know if you've ever been in an elevator. I have. But if you push the up button on the elevator when you're at rest, you accelerate upwards and you feel heavier, but you are not heavier. This and this are the same. You feel the normal force. Okay, now let's do one last case. What if you accelerate down? In this case, the gravitational force is again the same because you didn't change, the Earth didn't change, but the normal force has to be smaller so that the F net, I should have done this in one dimension, equals ma, but now a is in the downward direction. And so this would be the case of, let's say you're moving up and stopping. You would have a downward acceleration and you would feel lighter. Or if you're at the top and you press it down, you accelerate downwards to speed up and you would feel lighter. But in all these cases, you feel normal. Here you feel heavier. Here you feel lighter. But you never change your gravitational force. So we like to say your normal force is your apparent weight. Now what about on the surface of the Earth? Your normal force is not, your apparent weight and your normal force is not constant. Okay. But one of the ways we can deal with this, let's take this back. Let's say that let's make a fake force. Because suppose you are in the elevator and you feel this greater gravitational force, but you're staying at rest. And so in your mind, in the terms of this elevator, there should be some extra force acting on you. And that is the fake force. So the fake force is a force added, I'm not even going to write it down, a force added to an accelerating frame so that it looks like Newton's second law still works. So it looks like you can still say F net is equal to ma right here. Okay. So in order to do that, what I'm going to do is just move this ma term to the other side. And that means that I'm going to get a fake force. In this case, I will have a fake force. Acceleration is down, so I'd have a fake force pushing up, F fake. F fake equals negative ma of the elevator. In this case, I have a fake force pushing down because it's accelerating up. So in both those cases, now the normal force is, or the total force is zero by adding that fake force. And so this is what happens when you're in a car, right? You're in a car and you turn into the side. Actually, I had a car right here. Where'd my car go? Okay. And you're turning left. It feels like you're getting pushed to the right. That's a fake force, right? You're not actually getting pushed to the right. So the key here is I want to add a fake force to my rotating Earth. So the Earth is rotating. Actually, which way would be? I think it rotates this way if you look at it that way. This is the axis. This is the North Pole, the South Pole, the equator. And it rotates around. If you're moving in a circle, here is an object moving in a circle. Right here, it has a radius r, and it's moving this way with the velocity v1. A little bit later, it's right here, and it's moving that way with the velocity v2. Even if it's going at a constant speed, a equals delta v over delta t equals v2 minus v1 over delta t. So there is an acceleration just by turning. And it turns out that the direction of this acceleration is towards the center of the circle, and the magnitude is equal to v squared over r, which is also equal to omega squared times r, where this is the angular velocity. And we're going to use the angular velocity because we have the Earth right there. Okay, so what I want to do is draw a force diagram for both of these people with the fake force, and then we can solve for the normal force. So let me just redraw the Earth, the whole Earth. So here's my Earth. So it's rotating this way with omega. And we know that omega is actually 23.9 revolutions per day. No. One revolution is 23.9 days. That's what it is. No, hours. I was just so excited about the 23.9. So 23.9 is a sidereal day. It's how long it takes the Earth to actually rotate. If you wanted to use 24 hours, I think that would be fine. It's not a big deal. But then we can convert this to radians per second, which we will do. Okay, but it is rotating. So now let's suppose that I have a person right here. It's hard to draw stick figures sideways. So what forces are acting on this person? Well, I have the gravitational force, which is this way towards the center of the Earth. And then I have a fake force, right? So this person's moving in a circle around this way, so the acceleration is that way. So that means I have a fake force this way. F fake. And then the person's at rest in this frame of the rotating Earth, so I have another force, the normal force in. So now I can say F net in the x direction. Let's call this the r direction right here, because that's the direction of r. It's going to be equal to n plus F fake minus mg equals 0. So I can solve for n. N is going to be equal to mg, that's not equals, minus ff. And so now I can find the fake force. It's going to be equal to mg minus ma, where a is acceleration, and this is going to be equal to mg minus m omega squared r, where r is the radius of the Earth and omega is the angular velocity of the Earth. So at the equator, your parent weight is going to be smaller than the Earth's, than the normal weight, the actual weight. Now let's look at the other case up here at the North Pole. First, you may be saying, why am I standing there? Because there's no land. And that's right. You could stand on here in Antarctica. Okay, in this case, you're not moving in a circle. You're spinning around, but you're not moving in a circle. So there is no acceleration. So you just have mg, and then you have n. So up here, n equals mg. And so your weight is your parent weight. So, but here would be smaller. Okay, let's go ahead and find this. So let's say the radius of the Earth is 6.371. I wrote it down. Yeah, I think so. Times 10 to the 6th meters. And then omega is going to be equal to 2 pi, that's 1 revolution, in 23.9 hours. And I want to get that in radians per second. So I'm going to multiply, because g is in meters per second squared. So I'm going to multiply this by 1 hour over 60 minutes. And so 1 hour is 60 minutes. So when I multiply by that fraction, I don't change the value. So it's okay. You can do this. But the hour units cancel and I get radians per minute. Now I need to do the same thing. Let's say 1 minute is 60 seconds. And the minutes cancel. So I get the angular velocity is 2 pi divided by 23.9 times 60 times 60 equals, I'm going to do this in my calculator because I want to. Yes, you may think, oh, but Python's better. And you're right. Okay, so 2 times pi. I thought there was a pi button. Pi button. Do you guys like make fun of me for not knowing where all the things in this calculator? Oh, there's pi. Okay, 2 times pi. Now I need to divide by, parentheses, 23.9 times 60 times 60. Close parentheses equals. And I get 7.3 times 10 to the 1, 2, 3, 4, 5, negative 5 radians per second. And that might seem really slow, right? It might seem really slow because it's a low number. But you got to think that it takes a whole day to make one complete oscillation. So it's not really going really fast. Okay. Okay, now let's calculate. Let's say I have a 1 kilogram mass. So up here, N is going to be, let's call this N North Pole, is going to be equal to 1 times 9.8. It's going to be 9.8 newtons. So down here, it's going to be 1 times 9.8 minus omega squared times the radius of the Earth. Let's go ahead and calculate that. Okay, so I have omega squared right there. I'm just going to re-enter it because I don't know how to do that. Okay, 9.8 minus 7. Let's do it this way. 9.8 minus the radius of the Earth, 6.371, scientific notation button. Oh gosh, where'd that go? There it is. Times 10 to the 6th times parentheses, I'm not sure I'm doing it right, 7.3 scientific notation button, negative 5 close parentheses squared equals 9.7. Okay, I think it worked. 9.77. So you're just a little bit lower. Let's find out what percent this is. Let's divide that by 9.8. So 99.65%. This is 99.65% of your weight. Okay, now, what if you were up here? So I'm in Louisiana, and my latitude theta is about 30 degrees. So if I'm right here, then what's different? In this case, let's go ahead and draw the forces. The first force is the gravitational force, which is this way, mg. Now, the acceleration is this way, right? Because, no, I'm sorry. The acceleration is this way because that's the center of the circle. This person's moving in a circle like that. They're not moving in a circle the radius of the Earth. So the acceleration's that way. The fake force would be this way. I drew that too big. And so that means what would I have to do to make the total force 0? I have to have a normal force, and it actually has to be angled this way. Is that right? In. So it's not in the same direction. It's the up. What you feel is up, and these are not drawn to scale, is not in the same direction as the center of the Earth. If the Earth's completely spherical, which it's not, but let's assume it is. Okay, so in this case, how do we do this problem? It's kind of complicated. Let me redraw just that one person. I mean, at the rough approximation, you could say that the normal force and the gravity are in, the normal force is in the same direction. And that's probably okay, but I don't want to be probably okay. Okay, so here I have mg. I'll draw it big. Here I have F, the fake force. And then so this would be the normal force. Okay, so let's call this the R direction. So that's the angle theta. First, let's calculate the fake force. So the fake force is going to be, the magnitude of the fake force is going to be the mass times acceleration, which is omega squared times the radius of the Earth times, this is my radius, right? That's how big I am. So I'm going to use R cosine theta. That's the magnitude of the fake force. The direction of the fake force along the R direction. I only care, let's just find this along the R direction. I probably shouldn't have done it that way. So that angle is also theta. So let's call this Y. So F net Y is going to be 0 in this rotating frame. Not really, only in this rotating frame. I shouldn't do that. I should do it like this, I guess. Let's call this X. That just makes more sense. So F net Y is 0, right? Because the acceleration, in both directions, the net force is 0. So I have, no, let's do it the other way. Let's call this Y. Okay, so F net Y is going to be equal to minus mg, and then I have a component of the fake force, which is going to be plus the fake force times cosine of theta, right? Because that's that component. And then I have to get the component of this. Let's just say ny. Because I don't know what that is. That's a y. And that equals 0. So let's write that out as negative mg plus the fake force of m omega squared r cosine theta plus ny equals 0. And so ny is going to be equal to mg minus m omega squared r cosine theta. Now what about the x component? So in the x direction, F net x, I have a component of the fake force. It's going to be m omega squared r cosine theta. Oh, wait. Oh, I forgot a cosine theta. I had a cosine theta, another cosine theta, so this is squared. So now I have a cosine theta, but now I want the x component of that force, so I'm going to have a sine theta. And that's going to be, and then minus in x equals 0. So in x is going to be all of that stuff. M omega squared r cosine theta sine theta. So now if I want to find the magnitude of the normal force, n is going to be the square root of nx squared plus ny squared. Okay, so let's just write this out. I'm going to factor out the m. That's in every term, because this is my nx, that's my ny. Every term has an m. Then I'm going to have the square root of this squared. So it's going to be g minus omega squared r cosine squared theta squared plus omega squared r cosine theta sine theta quantity squared. Okay, so that's complicated enough that I'm going to make a plot of the apparent weight as a function of latitude from 0 at the equator to 90 at the North Pole. We can check right here. Well, we'll check it when we plot it. Because I know that we already calculated those two values up here. We should be able to check and see if we get the same thing. Okay, so let's switch over to Python. I know this looks a lot more complicated than you wanted it to be. You could just use this and say n is in the y direction, because I think this nx component is super tiny. But I just wanted to do it the way that I felt comfortable with. So let's switch over here to the camera. No, that one. Okay, so here we are. So let's enter in some stuff. I need the radius of the Earth. I do. I'm just going to call it r. 6.371 times, oops, why did I put a space? 371 times 10 to the 6th. Omega, I'm going to call it W, is equal to, what did I say, 7.3 times 10 to the negative 5th, 7.3 e negative 5. G is 9.8. I'm just using the scalar value of the, and let's say, let's make a graph. G1 equals graph. Title equals apparent weight. X title equals latitude. Latitude in degrees. I'll switch to degrees. Y title is going to be equal to apparent weight. In G's. Let's do it in G's. Right, so I'm going to divide by G, because otherwise I don't want to do it in newtons. That doesn't make any sense. Let's make it a little bit smaller. Width equals 500. Height equals 300. That's way it'll plot a little bit better. F1 equals G curve. Color equals color dot blue. So the G1 is my graph with the axes and stuff, and then F1 is what I'm actually plotting. So let's start with theta equals 0. And then d theta, let's say it's 2 degrees. So 2 equals 2. Yeah, that's fine. 1 degree. So it's just going to be 1 times pi divided by 180, because I convert to radians. Okay, so while theta is less than or equal to pi over 2, so I'm going to increase my angle until I get to the North Pole. So the first thing I want to do is to calculate the apparent weight. So I'm going to say N equals, and I'm going to divide everything by G. So this will be N in G's. And now I just have my equation right here. So I'm just going to write, I'm leaving off the M. I'm going to divide by mg. So the square root of parentheses G minus, I think the G is going to cancel, but that's fine. Omega squared, squared times R, and I'm pretty sure it does a square, not 2 raised to the 2R power, times cosine squared, so I'll say cosine theta squared, and then all that squared, and I did this wrong. Okay, I think that's right. Okay, so that's that one. Then I'm going to say plus omega squared, pull my keyboard, I can't see, squared times R times cosine theta times sine theta and see, that is that one. So that would be squared, and then I'm missing a parenthesis right there. I think that's right. Now I'm going to divide all that by G. So then it'll be in G's. I know that's terrible. Okay, now let's plot that. So I can say F1 dot plot the theta times 180 over pi, because I want it in degrees, versus N. And now I'm going to increase my value of theta. Theta equals theta plus d theta. If this works, I'm going to be super surprised, because I feel like I made an error somewhere. I should save it. And I don't know why it's been taking forever to save, but let's just run it. Oh, well, that worked. Okay, apparent weight in G's. So 0.3, that's not right. That's not right. Right, because we know the apparent weight when it should be 1. So I just have a typo in here somewhere. G minus omega squared R cosine squared theta squared plus, that is a square root, omega squared R cosine theta sine theta squared. What if I take away the G? 3? That's just not right. Oops. Let's see. Apparent weight. I can't back down now, can I? Okay. what can I do to figure out what's wrong? Let's just plot in y. So I'm gonna cancel this, and let's say in y equals, I'm writing it down, so it's going to be g minus omega squared times r times cosine squared theta. See, but it should just be cosine theta. Let's just say cosine theta, because I know that one works. And then if I plot that in y, let's see what happens. Okay, so see, here I'm getting the value that I expect. I get 9.8 up there, and I get point. But then if I multiply by another cosine squared theta, oh, in y, why is that why did I put a cosine? No, I shouldn't have a cosine squared theta there. That's the acceleration is m omega squared r cosine theta, period. It's not cosine squared. Why would I have another cosine? Oh, I did. I wanted to make that in the actual y direction because I rotated my axis. But then the acceleration is not 0. I bet down here if I change this, let's plot in x. In x. Then I'm typing my equation. In x is omega squared times r times cosine theta times sine theta. And let's make two graphs. F2 equals G curve. Color equals, I thought this was going to be like a super simple calculation. I thought it's going to be easy. I'll just crank it out just like the boss, right? And that didn't happen. Okay, so F2 dot plot theta times 180 divided by pi in x. Okay, so that one's super tiny, but now I need to, I'm pretty sure this has to be cosine squared. And you still see this is good. Oh, that's working now. Because that one's in y. That one's close to 9.8. Yeah, so that one is working. If I just copy this out. There. Okay, well, I'm not sure what wasn't working correctly. I think this is good enough. The nx component is super, super, super tiny. The ny does go to 0 as I get up there. So I think I'm pretty happy with this calculation. And you can see how the parent weight changes. Okay. Oh, I'll include the code down below.